So this is our last class. This is the last time I see you. So I'm going to see you on Tuesday on the final exam, which is going to be in this classroom, 10 minutes after, just come 7 o'clock, 7 p.m. till 9 p.m. And bring your laptop again, bring your ID, bring a calculator. So I'm going to have the review session Monday, May 2nd, 3:30 till 5 p.m. on Zoom again. So the usual Zoom link, it's on Canvas, but I will send you the Zoom link. If you can't come, it's fine. I will post a video. Go to the final module on Canvas and complete the final review. And final exam basically contains module 4, module 6, and module 7 material. Of course, module 2 is the fundamental for everything. So I'm not going to have direct question from module 2, but I mean, function notation, you have to be able to use function notation that's what just basically was a review. That was a fundamental module to build on, okay? Of course, we're going to use derivatives, which was module 5 as well. So review everything in module 4, including the homework problems, IMATS, module 6, module 7, quiz problems, recitation assignments, and additionally, the final review I posted on module 7. And here is a PDF file that you can see the review topics as well. So anybody has any question about the final exam? Final exam has about, what did I say last time? It's 18 questions, right? Or something like that. Actually, let me look at it again. So all the information about the final exam in the final exam module. So here we go. So 21 questions and with 28 items to answer. Okay. The practice problems are here, but again, I said the practice problems are not comprehensive. It's not like you think that you do the practice problem, then, oh, you're going to be prepared for the final. You have to review what you learned in module 4, module 6, and module 7 mostly. Okay. Right. Well, any questions about the final exam? Right. Well, so let's finish up our discussion about the fundamental theorem of calculus. So this is the worksheet. So we have this, we basically discussed the fundamental theorem of calculus, or review the fundamental theorem of calculus last time. So we know what rate the quantity is changing, and we want to find out how much of it we have. So in this particular problem, the rate of change function represents the rate of change of the elevation in 100 feet per mile. As a function of the distance from the coast. So we discussed that, for example, this point here, right? 1.5, that means 1.5 miles from the coast. The rate of change of the elevation is 200 feet per mile. So that means a little change in the distance from the coast, little change dx, then d over dx, right? The ratio of the elevation, right? The change in the elevation and the change in the distance from the coast is approximately 2. So that means if you change a little bit the distance near 1.5, just a little bit, let's say 0.5, then the elevation is going to change. It's basically double, approximately will double, right? That's what it means, right? From this information, we could build the accumulation in the elevation. We can build the elevation with bits of changes, right? And that's the integral. So you integral the bits of changes, which is rate times the little change in the quantity, little change in the distance from the coast, and you accumulate them, integrate them, sum them up, right? These are really tiny. And that's going to give you how much the elevation changes from A to X. A is the distance from the coast, and X is, again, is an undetermined distance from the coast. How much the elevation changes as the distance from the coast changes from A to X. We know, and that's what we started to discuss. This is what we call the elevation into basically as relation to the rate of change function as an anti-derivative, right? So this is the derivative, the rate of change function, and the elevation function is the anti-derivative. We know how to calculate this with the GC computationally, but we want to have a systematic way to calculate. So we need to be able to find systematic way to find anti-derivatives. We know how to find derivatives, rate of change, but we want to reverse the procedure and find anti-derivatives and calculate integral, which calculates net change in the quantity systematic way, not just with the GC, just with a systematic way with formulas as well. Okay, so after that, we said that the elevation, any x, where x is the distance from the coast, is an initial elevation, where a is a distance from the coast, plus how much the elevation changes from A to X. The integral expresses how much the elevation changes from A to X, where A is the distance from the coast, the starting distance, the initial distance from the coast to an undetermined value of X, right? So that's the meaning of everything you learned here, okay? So this is what you have to really remember when you go to Calc 2. You guys remember that? Understand that? From the rate of change, you could find out how much if you integrate the rate of change function, you could find out how much the function value changes, which is what we call as a relation to the rate of change function is an antiderivative. And from here, we could actually find out the function value, right? The function value, the elevation as a function of x. X is the distance from the coast, right? As an initial distance and plus how much it changed. So our journey is now how to calculate this integral systematic way, how to find anti-derivatives. And so just let me review it quickly. We started to find anti-derivatives for simple functions like polynomial functions, radical, x to the n, and we said, well, here is the basic integral rules. And this naked integral sign means that you're finding the antiderivative. That's an operator symbol, right? That's the opposite of or the reverse of the derivative symbol. So now you're finding the antiderivative. What is that function whose derivative is x to the n? That's x to the n plus 1 over n plus 1. And then n is not negative 1. What is that function whose derivative is 1 over x? So you're finding the antiderivative. So that's going to be ln of x, and so on and so on. All right, so we went through this, and then we did more complicated antiderivatives with 5x plus 3 over the raised to the power of 10. And we did kind of trial method. We applied a more complex power rule, right? And we just basically guessed the antiderivatives, and we tried it for simple functions like this. And then we drive a formula for that. Okay, so this is where we were last time. So making sense of derivative of accumulation function. So the accumulation function is an antiderivative, right? So this is the rate function, you know, the accumulated rate from 2 till x, right? Then you get the accumulation, the accumulated quantity. And whose rate function is e to the sine x. So this is an antiderivative of e to the sine x. So when you take the derivative of the accumulation function, since that's an antiderivative, then basically you undid the procedure, right? You didn't do anything. You just went there and then you came back, right? So that's going to be back. You go back to the rate function, e to the sine x. Everybody's okay with this? Did you guys practice this yesterday with Barbara as well? So now we're going with more complicated ones. So here I restated the fundamental theorem of calculus, which has two parts, right? One part is when you generate the accumulation function, the accumulated changes with the rate function. This is the accumulation function due to this rate function. When you integrate a rate function, you always get an accumulation, the accumulated in the quantity. That's an antiderivative. So that means when you take the derivative, you basically undid the procedure. The derivative of g of x is back to the rate function. Other part of the fundamental theorem of calculus, that means the integral of a rate function from a starting value a to an undetermined value of x expresses the net change in an antiderivative, right? From a to x. So that's f of x minus f of a. Right? So this is what we practiced in module 4 many times. Okay, so, and back to these two problems again, I review. What's the derivative of integral of 4 till x sine 3 cosine x dx, right? You don't have to calculate anything. Integral from 4 till x, that's an accumulation in the quantity which expresses the change in a quantity due to this rate function from 4 till x. This is a number that produces a number because it's a specific value. When you take the derivative of that, you're going to get 0, right? And this one is the same as I said before, just based on the fundamental theorem of calculus, integral from 4 till x, that's the accumulation function due to this rate function, which is an antiderivative of this function here, right? So if you take the derivative of it, then you just get 3 cosine x, right? Okay. All right, so now let's do a more complex version of the fundamental theorem of calculus. What would be the derivative of integral from -5 till e to the 4x, right? So e to the 4x is a function, is not x where we had before. Did you guys do this type of problems with Barbara as well last time? But anyway, so I'm going to do at least a couple of this type of problems. I think you're going to have one like that in the final exam, and you have few of these in the next IMATHES assignment, the last one. So let capital F of x represent the antiderivative. So let capital F of x be an antiderivative of radical 1 plus x squared. So this is. Then using the fundamental theorem of calculus, we could express the integral as what? The integral is what? Using the fundamental theorem of calculus, if capital F of x is an antiderivative of the radical function. So then what would that be? Using the fundamental theorem of calculus, that would be capital F, yeah. Yeah, again, the upper limit is e to the 4x, very good, minus Well, I haven't taken the derivative yet. Okay, I just write in, forget about the derivative. Okay, so we don't have this. Okay, I'm just rewriting it now. Okay, the derivative of that is going to be 0, right? But just the integral is going to be capital e to the 4x minus f of -5. Okay. Now I'm going to take the derivative. So term by term, derivative of capital f of x of e to the 4x minus derivative of capital F of -5. Okay, now, so I'm taking the derivative of capital F with which is a composite function of capital F and e to the 4x. I don't know what capital F is, okay? But I don't really need to, okay? I all know that capital F, which I know it exists, capital F is an antiderivative of the radical function. So if it's an antiderivative of the radical function, that means when you take the derivative of capital F of x, right? So f prime of capital X is what? The radical function, right? Okay, so when you take the derivative of capital F of e to the 4x, what rule do we have to use? Of course, we have to use this idea here, but also we have to use the chain rule, right? Because this is a function, it's capital, the derivative of capital F of x with respect to x is with radical 1 plus x squared, right? But I have to take the derivative of capital F of x with respect to x, and I have an inside function here, right? So when I take the derivative of that, I have to use the chain rule. So what's the derivative of capital F with respect to e to the 4x? Square root of 1 plus e to the 4x squared, right? Okay. So that's going to be square root of 1 plus e to the 4x and the square of that, because we're taking the derivative of capital F with respect to the inside function. Using the chain rule, still have to multiply by the derivative of e to the x, which is e to the 4x times 4. And that's it. Derivative of f of -5 is, that's a specific number, right? That's just going to be 0, right? So this is 0. So it really doesn't matter where you start this, right? -5, -10, or whatever. As long as you have a constant here, you're going to get always the same number or the same function. So here I generalize this formula or this idea, right? I generalize that if you have an integral expression and accumulation from a to a function, not x, not h of x, f of t, let's generate an accumulation function. When you take the derivative of it, the accumulation function, then you go back to the rate at the inside function. So that's going to be the rate at the inside function, h of x, and you have to multiply by the derivative of the inside function, which is h of x. That makes sense? Okay. So you don't have to remember this formula if you understand the fundamental theorem of calculus. You could derive it all the time, or just remember the formula. I don't think it's that hard to remember the formula if you understand what's going on. So without deriving everything I did before, if you want to find out the derivative of this function here, this accumulation function, So that's going to be the rate function, right? That's gonna be going back to the rate at radical x, right? Okay, the rate, because that's the inside. So that's gonna be ln of, ln of radical x. And then you multiply by the derivative of radical x, which is 1/2 radical x. And doesn't matter that what we have here, okay? So it could be any number. Any number in the domain, of course. So make sure you're going to get this problem completely right in the final exam. Yes?
Sorry, I just got a little lost.
Okay.
So what are we starting with? Are we starting with the accumulation function and basically solving for it for the limits, or?
So let me go back to here first, okay? So I'm going to take, this is an accumulation function, except the upper limit is not x, it's going to be a function there, okay? It's more complex, right? So forget about this dx now, I'm not taking the derivative. If I find an antiderivative, then I could calculate this integral as capital F of e to the 4x minus capital F of -5, right? If I find an antiderivative, I don't care what the actual antiderivative, but capital F of x is an antiderivative of this rate function, okay? So you understand it up till here, right?
Yeah.
Okay, now we're going to take that derivative of this more complex accumulation function. So that means you're taking the derivative of the difference of the antiderivatives, right? Okay. So now I'm going to take the derivative of the first function and the second function, you can differentiate term by term. This is a specific number. You evaluate a function at -5, that's a number, right? So the derivative of that is going to be 0. So now I want to take the derivative of this function, but I know that capital F is an antiderivative of the radical function, right? So I have to use the chain rule when I take the antiderivative because I have an inner function here, an inside. So derivative of capital F, the outside function, is the radical function with respect to the inside, right? So this is the radical 1 plus e to the 4x squared, right? And multiply by the derivative of the inside function. So this formula is just generalizing what I did before, right? So in the formula, this is gonna be f of t or f of w, right? This is gonna be the function f of w into the formula here. And then when you take the derivative, right, you go back to the rate function, right? So this is the rate, and h of x in this problem is e to the, h of x in the previous problem is e to the 4x, right? Makes sense? And then here you move, this is gonna be derivative of e to the 4x is e to the 4x times 4. And this part is 1/1 plus e to the 4x squared. That makes sense? So this part is e to the 4x times 4, the derivative of h of x, and this part is the derivative, or is the rate function, right? Because you take the derivative of the accumulation function, you go back to the rate function, evaluated at the inside function. That makes sense? So applying the same thing in this next expression, right? And then you take the derivative of the more complex accumulation function, right? You get back to the rate function, which is ln at the inside function, so ln radical x, and then you multiply by the derivative of radical x. Okay? So this is the derivative of radical x. Is it okay, everybody? Yes?
Is it okay to put -0 at the end? Or?
Yeah, it's okay. Yeah, that's not going to change. Definitely, I'm at the S in the final exam. I don't think you're going to have 0 there. Okay, but you can imagine you could do it and then you recognize it. Yeah. So this is just the formula. Again, just generalizes the idea, right? So here is the accumulation function, which is the rate function due to this rate function that generates an accumulation function, which is an antiderivative of f of x, right? So once you take the derivative of that, then basically you cancel, you undo the procedure, you go back, you get back to the rate function. Here is the more complex accumulation function because you have a other function in the top instead of x, right? And generates an accumulation, a more complex accumulation function. So when you take the derivative of that, you get back to the rate, right? So this is again a rate function. So this is rate. And so when you take the derivative of that, then you get back to the rate function at the inside function at h of x. So just have to substitute h of x here, right? And then you take the derivative of the inside function. Does it make sense? Right, so we're going to still practice. I have one more problem like that, and the quiz, one of the quizzes I assigned to you, that's again practices this problem, this type of problems. So making sense of again more complex expression. I'm going to show that the integral from a to b f of x dx, if you reverse the limit of the integration, right, that's basically you get the same thing except you have to get the negative, the opposite of that. So then you have to multiply by -1 to get the integral from a to b. And why is that? So let capital F of x be an antiderivative of lowercase f of x. So this integral is going to be f of capital F of what? F of the top, f of b minus f of a. And this integral is going to be capital F of a minus f of b, right? So you establish this relationship, right? So when you interchange the order of the upper and the lower limit in an integration, then it's just, it's gonna be a -1 multiple, right? So this is the same as -1 times f of b minus f of a, which is this relationship right here. So what's the rate of change of the accumulation when x is on the bottom, right? You start x and to the 5. This is all just manipulative exercises. And in Calc 2, you're going to have a lot of integrals or whatever. So you have to be pretty good about this, how to manipulate this. So that's going to be the same as negative derivative of integral from 5 till x e to the cosine t dt, right? I interchanged the upper and the lower limit, and I multiply by -1, and I take the derivative of that. What's the derivative of this function? Derivative of the accumulation function due to this rate function from 5 till x. So what's the derivative is e to the cosine x and multiply by -1, right? So that's going to be negative e to the cosine x. Right, any questions? So this is the form you should remember. Yeah. Well, it is because I mean the chain rule always use it. You just multiply by the derivative of x with respect to x, which is 1, right? Okay. Yeah. So you're using this chain rule, but it's not really chain rule because derivative of x is not a the identity function, right? So we see that, okay? So you're multiplying by derivative of x with respect to x, which is 1. If
x squared
multiply by, yeah, then that would be, if that would be x squared here, then would be x squared here and multiply by 2x here. Okay, that's another important formula. It's once you know the fundamental theorem of calculus formally, then you could prove it easily. Capital F is an antiderivative of lowercase f. So this is my rate here. So this is gonna be capital F of B minus capital F of A. This one is capital F of C minus capital F of B. So that means if I break up the integral from A to B, f of x dx, right? And integral from B to C, f of x dx. And what do I get? That's f of integral from A to B, f of x dx. So that's gonna be f of B minus f of A, right? So this part here is f of capital F of B minus capital F of A. And this part here is capital F of C minus, let me use a different color for that. I think I need to buy a new Apple Pencil. Just getting, or just the head of it because it's always hard to write with it now. Capital F of C minus capital F of B. So that's capital F of C minus capital F of B. And that means capital F of B and minus capital F of B cancels out, and you get capital F of C minus capital F of A, which is the same as integral from A to C. That's capital F of C minus capital F of A. So we have proved that you could break up the integral from A to B, some intermittent value. And B is going to be some intermittent value, integral from A to B, B to C. Then it's going to be integral from A to C. All right, well, any questions? Is it okay? All right, now the last problem is more complex, right? Because you have a function on the bottom and a function on the top, right? But we had a function on the top and a number on the bottom, or vice versa. We had a function on the bottom and the number on the top, but we never did function on the bottom, function on the top as well. All right, so what do you think? How should I approach this problem? Well, don't guess the formula. Let's do it, systematically. How did I do all these formulas? Using the fundamental theorem of calculus, right? So let's say capital F is a antiderivative of ln of x, okay? So let's see. Assume capital F of x is an antiderivative of ln of x. So then, how can you express this integral using your antiderivative? And you have this rate function, right? Using the antiderivative capital F. How can you express the integral is? Capital F of square root of x, right? Minus capital F of sine x, right? Okay, so that's the fundamental theorem of calculus, right? Okay, now let's take the derivative of that. Radical x minus capital F of sine x. So I'm going to take the derivative term by term. Except now none of them are constant, right? Because both are functions here. So in both cases, I have to use the chain rule, right? When I take the derivative of it. So let's do the derivative of the first one, right? So derivative of capital F is ln, right? So this is my rate here. So this is rate. So derivative of capital F is gonna be ln with respect to the inside function, very good, square root of x, and then you're not done yet. You multiply by the derivative of the inside function, which is 1/2 radical x, and minus, and you do the same thing, derivative of capital F is ln, right, because that's antiderivative, so that's gonna be ln of what? Sine x. Ln of sine x, and you multiply by cosine x. That's the rate function, exactly, yeah. So then when you, so capital F is an antiderivative of ln of x. I don't know exactly what it exists, okay, you could find it, but we don't need to know it because anyway, you're going to take the derivative of it, which is basically going to reverse the procedure. We don't know, we don't need to know exactly what it is, okay? I just know it exists and I'm just going to use that, capital F as an antiderivative for ln, right? So when I take the derivative of it, so I basically reverse the procedure, then I go back to ln because that was the rate at this function, right? And multiplying by the derivative of the inside using the chain rule, right? All right, well, any questions? I'm going to start a little bit of the review and again, talking about accumulation and relation to area.
Barbara did a lot of that yesterday.
With this one or
She didn't go over integrals yesterday.
so what,
She just did like final review, like accumulation graphs.
okay, well, that's good, but did she do anything like this, what we did now?
Did she?
Okay, so, I mean, I'm sure in the recitation, probably you have 1 or 2 problems like that, okay? Yeah, but anyway, I think I did like 4 or 5 problems like this. That should be enough, right? So if you practice the quiz problem and you practice your IMATHS problem, then you should be, I don't think this is the hard part. That's pre-procedural, pretty much. So Barbara actually make the connection between accumulation and area. Did you guys calculated area in recitation too?
Not really.
No, well, that's what that's mostly you're going to do that in Calc 2, area and volume, but let's see. So again, I have the rate of change function. This is the rate function here. That's should be on Canvas, right? With the announcement, I put it on the announcement I sent at beginning of the week, and what also should be on the where I put all the lecture notes. I think this is the last lecture notes probably there. So accumulation and area. So here's the rate of change function. Think about the velocity function. Velocity is always easier to visualize. Okay, so this is the rate of change function, velocity function, and you want to find out how much the moving object traveled, the distance traveled by the objects. What do? We have subdivision, right? So here is, we're going to find the accumulation from, it seems like 1 till 4.2 or something like that. This is an X value here. This is my initial value is 1. And X is, in this particular case, the current value of X is 4.2 or something like that. How do I build my accumulation? We create constant rates. What we did is the left-hand point, we use the left-hand point of the subdivision. So we have delta X subdivisions here, right? So this is delta X, delta X, delta X. We use the left-hand point, the rate, and define constant rates. Doesn't have to be theory. It just makes the calculation nicer, and just the formula is nicer if you use the left-hand point for the accumulation function. But the idea is we create constant rates in each delta X interval. Why constant rates? Why do we use constant rates? Because if your car travels with a constant rate, can you calculate the distance traveled by the car? Yeah. So for example, your car travels 70 miles per hour for 3 hours, constant 70 miles per hour. 3 hours. What would be the distance traveled by the car? Is 3 times 70, right? Constant rate is good because you can deal with it, right? So that's why we're creating constant rates here, right? So if I want to find out how much the distance traveled by the car in the first interval, this is, let's say, time, right? So this is my rate. How do I calculate that? Dx, the time interval, the velocity is, let's say, R1 of X here, or yes, so I multiply the time by the velocity, right? Okay. So which is R1 times, or R1, that's the value, okay? So that's R1 times delta X. So that's gonna be the distance traveled by the car during this time interval right here, Okay, that's right here. I'm building my accumulation. This is my accumulation, the distance function. It's right here, okay? But if you go back to the rate function, R1, which is the function value here, times dx, that's going to give you the area of this rectangle, right? So that's the area of this rectangle right here.
And that was R1 times dx.
That x actually, that's, we have the fixed subdivision, yeah. That's R1, right, okay? It's an approximately, right? So that's R1 times delta x, that's the area of this rectangle, right? R1 is the height, and delta x is the length of the subdivision. It makes sense? So does it make sense, right? So R1 is the height of this, that's the rate, we use the rate, right? So approximately the rate here, this is the rate function. So I'm using the value of the rate function, which is the height of this rectangle, multiplied by delta x, which is the length of the subdivision. It's a tiny interval here. I multiply this together, I get how much the car traveled physically, right? If it's velocity, it's right here. But it's also, I get the area of this rectangle. So let's move to the next delta x interval. The next delta x interval, we have R2, as we use the constant rate R2, right? The rate. It was in the left-hand point what we did, right? So R2 is the left-hand point, that's the rate. That's the velocity multiplied by delta x. Multiplying by delta x, what do you get, right? So this is the time interval. The time interval is always delta x multiplied by the velocity. Then you get how much the car traveled during this little time interval. It's right here, right? So additionally, this is how much it's traveled from the head, how much it traveled from here to here, from here to here. So then we building how much the car traveled from first delta x interval, second delta x interval, right? We are right here. But again, R2 times delta x is what? Is the area of the second rectangle right here. Okay, let's do one more, and then I think you get the idea. If you move to the next delta x interval, the next delta x time interval, again, theoretically, we don't have to have the same subdivision, the length of the subdivision doesn't have to be C, it has to be small, okay, to approximate. It's convenient to have the same subdivision because it makes the calculation easier, right? If you use, rather than using different type of subdivision, right? That's why we're using the same. So the next subdivision, again, this is a tiny time interval, delta x. And again, we're going back to the rate function and approximate the velocity here, right? And we use that value, it's R3, right? So the third delta x interval, R3, is the velocity, the rate, multiplied by delta x. In physics or in application, if this is the velocity function, that's going to tell you how much the car traveled additionally on this time interval, which is right here. So as you add those up, accumulate them, you're going to find out how much the car traveled from here to here, right? So it's accumulate bits of little velocities or bits of little distances, right? But again, geometrically, this is the area of that rectangle. So the sum of the areas of the rectangles created on the rate graph. Okay, so let's write this down. That's the sum of the rectangles, sum of the area of the rectangles, sum of the areas of the rectangles created on the rate graph. And here we're getting, so here on the accumulation graph, so that's the accumulation from A to X, which we usually denoted by A of X. So that's gonna be R1 times delta X plus R2 times delta X plus R3 times delta X, and so on and so on. That's the net change in the function value. So the net change, the approximate net change from A to X. How much the car traveled from the initial time to the final time, right? Okay. So what happens if I refine my subdivision? If delta X approaches 0, what happens then? What happens on the read graph and what happens on the accumulation graph? If delta X approaches 0. Then what would you get this? This is gonna give you the exact area under the grade graph, and this is gonna give you the exact accumulation, okay? So.
Sorry, changing X to essentially 0. What did
Right.
you say that would do again?
So here, I'm gonna write it again.
Okay.
Yeah, I'm gonna write it. So here is the next page. You could see that as delta X approaches 0, right? So this is as delta X approaches 0. That means as delta X approaches 0, the area enclosed by the rate graph and the X, we obtain the area enclosed by the rate graph. Let me just say the graph of the rate function. By the graph of the rate function and the x-axis from A to X, from the initial value to the final value, from A to X. And on the accumulation graph, okay, so we get the value, right? The accumulation function, the distance, that's the net change. As delta X approaches 0, we obtain here the exact accumulation, exact net accumulation, which is the integral from A to X, the rate function, or T dt. So integrals can be used to calculate areas. And that's you guys going to explore that pretty much in details in Calc 2. Areas, volumes, basically the same idea, some kind of slicing. and you add up bits of little volumes or bits of areas. Yes?
Is there going to be anything like this in the final?
In the final. So, I mean, you have to understand the area, but the accumulation, if you understand the area, accumulation connection is going to really help you, which I'm going to do some problems like that on the review class. Because once you have the rate graph, basically the area is going to, if you visualize the area, is going to tell you how much the car travels, right? And how much the temperature changes, or how much you're adding to the volume changes or stuff like that. So the visualizing and understanding the area accumulation connection, it's very useful. Yeah. So this is what I basically said before. Here we have the rate of change. If f lowercase f of x is the rate of change function, that this area under the rate of change function from 1 till x, that represents the accumulation in the quantity, this integral expression, and which is the same as the area. So as I said before, we could use integrals to calculate areas now, okay? But that's a secondary meaning. So for example, if I want to calculate the area enclosed by this curve here, which is g of x, what should I do? Could use integral to calculate. So let's say this intersection point here is x1 and this one is x2. Now, how can you calculate the first red segment? This is the first one, this is the second one, and this is the third one here. The first Rex, just how could you calculate? We're not going to calculate it, but with an integral. Can you write an integral which calculates the first red area? Integral from, what is the starting value there? So like negative 0.5, right? Yes, so that's going to be negative 0.5 till x1, which is the point of intersection. The function, which is g of x, dx. How about the second one? Can you write a formula which calculates the area of the blue region here? What would that be? Integral from x1 to x2, g of x, dx. But this integral, what's the value? What's the sign of this integral? Negative. So to get the area, I have to multiply by negative 1, okay? All right, so this is negative. So I'm multiplying by negative 1 to get a positive number, because the area, I just want to have the area, I have to have a positive number. Okay? Right. So that's negative accumulation. And how about the next one? Integral from x2 till 4, okay, good. 4, yeah. Oh, it actually says it, right? So gx dx. And that's positive. So to get the area enclosed by this curve, you need to calculate this integral. Right, so finally, how do we calculate integral? How do we calculate physically something like that? You have to know antiderivatives. So let's do one problem like that. So here is, well, here you could actually, yeah. So we already solved this problem here. Oh no, this is actually here. Let me get a. All right, here we go. Find the area between the curve g of x equals 200 e to the 1/3 x and the between the curve and the x-axis between x equals 2 and x equals 4. Exponential function, increasing exponential function, something like that. So this is x and g of x. And we want to find out the area enclosed by the curve and the x-axis from 2 till 4, something like that. X equals 2 till x equals 4. Right, how can we do that? What would be the formula which calculates this? The formula would so can you set up a formula which would calculate the area is integral from where to where? 2 till 4 of what? 200 e to the 1/3 x dx. Again, look at this more closely. Again, so you could think of it. I mean, here is really just recalculating area, but it's still a weight function, right? It's kind of, you can think of it as a weight function. But think about it. Once you have the subdivision, what's the meaning of this expression behind the integral? Dx is an infinitesimal subdivision, right? So this is dx, right? I can't really draw infinitesimal subdivision, right? Because you don't see it, right? So let's see, this is dx, an infinitesimal subdivision, and that's where its x is, right? Where x is a tiny changes. And the value of this function here is g of x, right? Which is, so g of x equals 200 times e to the 1/3 x, right? So this product here, right, gives you the area of this infinitesimal or this infinitesimal rectangle, right? So this one is the basically 200 times e to the 1/3 x times dx, the area, approximately a tiny area of that thin rectangle. So g of x times dx is approximately the area of a thin rectangle with base dx, which is infinitesimals, and height g of x, right? Which is the function. So this integral, what does that do? This integral is integrate them together, right? Add them up, right? So integrate this little, so you could think of this basically as just straight lines, right? Okay, because they don't have really a length, right? It's infinitesimal, these are just lines here. Okay, the integral is going to basically add those up. All right, so how do we calculate this? How do we calculate using the fundamental theorem of calculus, right? We need to find an antiderivative, okay? Right, so find an antiderivative. Of 200 times e to the 1/3 x. Okay. Well, What would be an antiderivative of this function? Again, it's an exponential function, just again using trial method. We have a constant multiple, so we're gonna keep that, okay? So 200. Now what would be a good, what do you think? Like, I mean, you know already derivatives, right? So you know the derivative of exponential function with a linear exponent is itself times a constant multiple. So what do you would be the first guess for the antiderivative here? Yeah, that's a good one. So let's try e to the 1/3 x. Okay, then let's take the derivative of that. So try. So we're gonna try this. So let's take the derivative of that. So what do you get when you take the derivative of it? You got 200 times e to the 1/3 x times 1/3, right? Okay, so we have this extra 1/3 here, which we don't want to have because I don't have the 1/3 here, right? So what would be by next try then, right? For antiderivative. So when this one doesn't quite work, right? 200 times e to the 1/3 x, because when you take the derivative, I got an extra 1/3 multiple. So how should I adjust my antiderivative is multiply by 3, right? So that would be 600 times e to the 1/3 x, and that would work, right? Once you take the derivative, that's really an antiderivative. So this one would work. So let's solve this integral now with our correct antiderivative. So this equals, so using our antiderivative is 600 times e to the, substitute the upper limit, which is 1/3, 4/3, minus 600 times e to the 2/3. And this is the value of this integral, okay? This is the area. Well, once you put it in your calculator with e, that's going to give you a decimal. So this is the area, and that's how you could calculate integrals using antiderivative. So all Calc 2 class is going to be how you start is a lot of procedures how to find antiderivative using the integral by substitution, integral by substitution, trigonometric functions, all technical part of integrals. So that's what you practice, and how you calculate volume of an object or area of certain objects, and you're going to use integrals for that. All right, well, I'm going to stop here now, and then you could work on your quizzes together. There are 3 quizzes I give you, but I don't think they are hard. So you should do them. Basically, it's like a preparation for the final exam. There's 2 due today and 1 tomorrow, and your assignment, IMATHS assignment is due today too. Yeah. Stop the coming. Just let me stop the recording, okay? Yeah.